Welcome to subsequent control basics classes. Today's topic will be about the object's responses and the error in control system. Let me remind you that the transfer function of an object is the ratio of the output to the input of that object. And in today's class, we will introduce the transfer functions of basic object models. One needs to remember them in order to use them in tasks. The first object is a proportional object whose transfer function is simply k, where k is the gain. As one can see, the gain occurs in every object, in each case in numerator, also in the other objects, which I will show in a moment. The second object is a first-order inertia object. This expression 1 plus st in denominator is called inertia. A new parameter also appears here, namely the time constant. The next object is a 2 inertia object. In this case, we have two different time constants. However, based on the transfer function, we see that if we replace t1 with t2, nothing changes. Therefore, it is impossible to indicate which time constant is t1 and which is t2. The notation mainly serves to emphasize that their values are probably different. The second-order inertia object, shown at top, is similar to the 2 inertia object, but differs from it in that here the two time constants are assumed to be the same. Subsequent example is nth-order inertia object, where the inertia in denominator is raised to the nth power. There is also a new parameter, that is the inertia order. The next object is an oscillator object. In this one case, I do not require you to remember the transfer function formula. If you need to use it, it will be given in the task content. Moreover, we are dealing here with two new parameters. This is the damping xc and the natural resonant angular frequency omega n. Damping takes values from 0 to 1. If xc is equal to 0, then we have no damping, and the response of such an object will be in the form of constant oscillations. However, for xc equal to 1, we have full damping, or critical damping, and from the formula one can see that such an object is a second-order inertia object. Next is the ideal integrating object. Integration is that lonely s in denominator. Another name for integration is astatism, which may also appear in tasks. Below, we see a real integrating object, that is, an object in which inertia additionally appears in denominator. At the bottom, we see a derivating object with inertia. This derivation is that lonely s in numerator. The ideal derivating object is considered in the script. However, in practice, there cannot be an object with the degree of numerator higher than the degree of denominator, which is why I left it out of this list. And the last object is the object with the lie. Please do not confuse this t0 with the time constants. This is a delay. What are all these objects for? First of all, these objects should not be associated with any real objects, items, things. For the same real object, for example a car, we can have several different models of control objects, depending on which signal we consider to be the input and which one is the output. But by using transfer functions, we can ignore the actual processes that take place in a given object, whether it is the speed of a car, the level of liquid in a tank, or the temperature in a nuclear reactor, and focus on selecting the appropriate control method for a given object. Additionally, please keep in mind that the presented object models are not all possible, because they can be created freely. At the bottom of the slide, one can see the transfer functions for a 2 inertia object with astatism, for a fourth-order inertia object with derivative, and for a free inertia object with delay. Based on the object name given in the task, one will need to be able to write the appropriate formula and perform calculations. In the first type of tasks, you will need to calculate the object's response, that is, the formula of the output signal. Below is the formula that fortunately we won't have to use. And this is another example of the fact that in the space of a complex variable, the operations performed are simpler, because the output signal y of s is equal to the product of the input signal and the transfer function of the object. Therefore, to determine the object's response, one will need to calculate the inverse Laplace transform of y of s. If the input signal is a unit step, the response of the object is called a step response, whereas if the input is Dirac impulse, then the response is called an impulse response. One can use the formulas provided here, but one can also derive them each time. I prefer the latter so that I can remember fewer things. The second type of tasks will concern the error signal in the control system. It will always be a system with negative linear unity feedback. Error is the difference between the input and output of a system. Here on the slide, the description in the time domain is shown, but it could just as well be a description in the domain of the complex variable s. And to get the error signal, we will have to use the inverse Laplace transformation again. The last type of task will require calculating the steady-state error, that is, the error value as time approaches infinity. We will be using a property we learned in Laplace transformation class, the final value theorem. Of course, it must be remembered that for the final value to exist, all poles of the product s times e of s must be placed in the left half plane of the complex variable. However, in the tasks I have prepared, there will be information that it can be assumed that the final value exists, so there will be no need to check the pole's position. I will show you how to get e of s in specific tasks. I would also like to remind you that this is a topic from which I have provided you all the possible tasks that may appear on the test or quiz. It is worth taking advantage of this. In addition, as you have probably already noticed, a very important element of most tasks will be the ability to calculate the inverse Laplace transform. So if someone has not yet mastered the material from the previous classes, it is better to go back to them. On the other hand, if you know the inverse Laplace transformation, you should have no problems with the current topic. The content of the first task is calculate the step response of the object with transfer function As for the step response, W of s is equal to we know that the output function y of s is equal to If the task requires calculating the object's response, it will always be a response in the time domain. Therefore, the response in the complex domain must be converted into the response in the time domain. It is therefore necessary to use the inverse Laplace transformation. I remind you that if anyone would like to learn more in the context of the inverse Laplace transformation itself, please return to the previous topic. The content of the next task has been given, and it reads: find the response of the derivative type object with inertia to an input w of s. Assume the gain is 2 seconds and the time constant is 5 seconds. The transfer function mentioned in the task content is the gain is the parameter k, and the time constant is the parameter t. So similarly to the previous task, we have to calculate the object response y of t, but we start with y of s. It is not necessary to write this short formula every time, but I prefer to record it each time for clarity. As you can see, all the special cases of the inverse Laplace transform can be expected in these tasks. Here we are dealing with a case that I just mentioned in the previous topic. We need to create a situation where denominator is a real number. So let's multiply by the conjugate. The content of the next task is: there's a system with negative linear unity feedback and with a transfer function g of s in the main path. Calculate the steady-state error if the input of the system is a unit step. It can be assumed that the steady-state error exists. We should start by understanding the content of the task. The system in question is such a system. The important signals for us are input, output, and error. The steady-state error is the final value of the error in the time domain. We will not need to check the pole's position, because we know from the task content that this final value exists, so we need function e of s. To determine it, we will need two equations in the system. Let's start with the object equation. Everyone should remember by now that transfer function is the ratio of output to input, where the output is y of s and the input of this object is e of s. I rearrange this equation to get the output. The second equation is the summation point equation, which implies that if I substitute the expression from the previous equation for y of s, I get I move everything with e of s to the left side. I pull out before the brackets, and divide by this bracket. This is the equation for the error function in such a control system. I don't try to memorize it because it takes me very little time to derive it, but if someone wants to use this formula from memory, they can. However, each task that requires this formula has the time for its derivation included. The transfer function is given in the task content, and the input signal is a unit step. So, our steady-state error is equal to In most cases, it will be fastest to simply substitute the value without any unnecessary transformation of the expression. And this is the steady-state error. That is, the difference between the set signal and the output signal will be equal to 3/4. If we simulate such a system, we will also see that this is exactly what happens. We therefore see that the actual steady-state value of the error signal is 3/4. The content of the next task is: in a system with negative linear unity feedback and transfer function g of s in the main branch, a signal w of t is fed to the input. Determine the error e of t. Let me start by deriving the error in the system. This time the input signal is given in the time domain. Therefore, the ability to calculate the Laplace transform will also be needed in this task. Let's calculate E of S. We have to find the error signal, so we simply have to calculate the inverse transform of E of S. Once again, if anyone is still having problems calculating the inverse Laplace transform, they should return to the previous topic. And if there are problems with calculating derivatives, you need to go back even further to the course in which these issues were discussed. If the task specifies that the result should be presented as a sum of the components without unnecessary brackets, then writing something like this at the end will be treated as a misrepresentation of the result. Task content. Calculate the impulse response of a second-order inertia object with derivative. The input signal is a Dirac impulse, so its transform is the transfer function of the object is the output is therefore The content of the next task is: an object with transfer function g of s is given. Calculate its response to the input signal w of t equal to t. The Laplace transform of the input is and so on. There is no any depth in these tasks, this is just another example. In the system with negative linear unity feedback, the main path contains the object with transfer function g of s. Calculate the steady-state error if the input of the system is w of s. It can be assumed that the steady-state error exists. I will start by deriving the equation for E of s. We are interested in the steady-state error, so I use the final value theorem. It turns out that in this case we cannot immediately substitute the value because we will get an undefined symbol. So what should we do? We can use L'Hopital's rule, but converting the entire expression to a single fraction bar and calculating the derivative will take quite a long time. In these tasks, the simplest transformation will be such that the variable s reduces. A unit step is on the input of a system with negative linear unity feedback. Determine the error signal E of t if there is an object with transfer function g of s in the main branch of the system. As usual, I start by deriving the formula for the error. At the input we have a unit step. So the error function is equal to where we have equal degree of numerator and denominator. In the next task, we will calculate the response of the object g of s to the signal w of t. we need to start by representing the input signal in complex variable domain. Let me remind you that in order to apply a delay, in every place where the variable t appears, there must be the same dependence as in the delay, which in this case is t minus 2. The rest is as usual. I would like to remind you that we have a special approach to delays. The content of the next task is: a free inertia object with derivative is located in the main path of a system with negative linear unity feedback. Calculate the steady-state error if the input is W of S. It can be assumed that the steady-state error exists. Calculate the steady-state error in the system with negative linear unity feedback and transfer function g of s in the main branch if w of t is the system input. The beginning with no change. The content of the last task is: determine the response of the integral type object with inertia to the input signal w of t. So we are dealing with a standard situation where we are interested in the output signal. The problem here is the delay in the input signal, so let's start the calculation from this input. Again, to use the delay, one needs to have the same expression that is in the unit step argument in every place where the variable t appears. Then input without delay is so our input signal is the object is the first order inertia object with integration, that is I will reduce everything to a common denominator. In the presented solution, several calculations in the middle were unnecessary. That is, when we already calculated W1 of S, one could proceed directly to calculating the underlaid output. But given the volume of the entire task, this is not a big saving. And that's all I wanted to show you during today's classes. Thank you very much for your attention and have a nice day.